I think you did not turn on your mic yet, Ajahn.
Sorry. Okay. Yes, I forgot to turn on the microphone. I'm sorry about that. Okay, you should mention that to me a little earlier. Okay, sorry about that. So we'll continue from last time, in which we have seen that we can compute our element stiffness matrix in parametric coordinates. So in parametric coordinates, you're going to have this domain of integral from -1 to 1 in both c and eta coordinates. Okay, and based on this domain, we are going to apply the concept of numerical integration to help us with the computation of this element stiffness matrix. Okay, so let's talk a little bit about the concept of numerical integration. Okay, so we'll start by looking at one-dimensional case as usual. When you compute an integral in one dimension, for example, if you have a domain of x from -1 to 1 like this, okay, when you're computing this integral right here of a certain function f(x), what you are basically dealing with is trying to compute the area under this curve, right? Okay, so now if you don't want to compute this analytically, meaning that you want to approximate this area instead of having to compute this analytically, but you just need to obtain this area by using some kind of approximation. You can do so by doing several different schemes, right? For example, you can say something like, okay, I can pick a certain point here on my function and use this point as a representative value. Okay, and then I can also compute the area under this representative value, which is going to be this area right here. Okay, so this area would give you the approximation of this integral right here. Okay, so this is one way to do it. So by selecting a point here on this curve and then use that point as a representative value to compute the area under the curve. Okay, or I can also, instead of picking just one point like this, I can pick 2 points, right? So I can pick this point here and here, okay, as my representative points, and then use this point to compute the area under the curve as well. So I would get this area right here, okay, and this area right here. So if I sum these 2 areas up, right, so I also get the approximation of my integral as well. So this is the basic idea behind numerical integration. You want to somehow approximate the integral or the area under the curve by using certain representative values of the function at a certain point, okay, and then use that representative value to compute the area under the curve instead of having to do it analytically. Okay. So this is the idea. So you can see that first of all, you need to have this point, representative points, which will be called sampling points. So this will be called our sampling point here. You can have 1 sampling point, okay? You can have 2 sampling points, 3 sampling points, or whatever sampling points you like to have, okay? And once you select your sampling points, you can find the value of the function at this sampling point, okay? So for example, if this is called sampling point A, then you can find the value of the function here, which would be fa, right? And if this point is at minus a, so this would be your function at f minus a, okay? And in order to compute the approximation of this integral, you need to find this area, which would be fa multiplied with this width of the base. Okay, so this is the base, or the width of the base of your domain, right? So in order to compute this area right here, so you just multiply this with w, okay? And if this, so your w, so you get something like this, right? Okay. Now, if I have only one point, okay, so the same idea still apply. Okay. So if I select one point, for example, if I select a point here, okay, so I can use my sampling point as x equals 0, right? And in order to compute the approximation, now I would need f0 multiplied with the width of the base, right? And in this case, the width of the base would be this width right here, okay? Okay. So in the first case, my width of the base is equal to 1, right? And in this case, my width of the base is equal to 2. Okay. So depending on the number of sampling points you're using, the width of the base would vary. But you can see that the summation of all this, right? Depending on how many width of the base you have, the summation of them must always be equal to this right here, right? Must always be equal to the original domain in which you are computing the integral, which in this case is from -1 to 1, which is equal to 2, okay? All right. So the summation of your wave would always be equal to this case. All right. So based on this concept, right, we're gonna try to find the sampling point which would give us a close approximation of the exact integral. Okay. Now, in doing so, you need to know how your original function look like. Okay. Okay. So in this example, I'm going to start by looking at this function right here, okay, which is a polynomial of order 3. Okay, so it's a cubic function in this case. Now I'm trying to find the sampling point which will closely approximate as much as possible the exact integral of a cubic function. So how can I do that? Okay, I can set up this objective function, right, which is the discrepancy between the exact integral and the approximate integral, which I will get from using sampling points. Okay, in this case, suppose I have two sampling points like this at x equals a and minus a. Okay, so I'm going to use this as the representative value for my function. Okay, so the approximate integral would look something like this. Okay, now I would like this approximate integral to be as close as possible to the exact integral. Now in this case, because I know what the function looked like to begin with, right? It's a cubic function in this case. So I can start by computing the exact integral, okay? So if my original function looks like this, okay, I can compute the integral of this function from -1 to 1 as this term right here, okay? So this is my exact integral. Now for the approximate integral, I would follow this scheme, right? So I need to find the value of my function at x equals a and x equals -a, all right? And then plug that back into the approximate integral, so I would get something like this. Now, my objective function is to try to minimize the discrepancy between these two terms, okay? So you can do so by solving a minimization problem. So basically, you try to find the derivative of this with respect to the variables that we're dealing with. Now, in this case, we have two variables, z0 and z2, right? So you are computing the derivative of your objective function with respect to z0, set it to 0, and then do the same thing with C2 and set it to 0, okay? So by solving this equation, then you would get W equals to 1 and A equals to plus and minus 1 over square root 3, okay? So in this case, you can see that if you use the sampling points at this particular location right here, your approximate integral would be equal to the exact integral, okay? So meaning that by using these sampling points, you can exactly integrate, or you can compute the approximation to be equal to the exact integral of a cubic function, okay? All right. So based on this concept, all right, you will see that if you have a polynomial of this order, you can use n sampling points to exactly integrate this polynomial, okay? Which in our example, we use 2 points, right? So 2 points can exactly integrate a polynomial of order 3, right? Now, if you use 3 sampling points, then the order of polynomials that you can exactly integrate would go up, and it would go up to 2 times 3 minus 1, which is equal to 5, okay? And for 3 sampling points, you can also find the sampling point which would give you the exact integral for the polynomial of order 5, right? And you will find this set value right here. Okay. So again, for 3 sampling points, we have 3 different locations, right? 1, 2, and 3 right here. So again, if you think of it, then you are basically subdivide your approximation into 3 parts, right? For each sampling point. So this is the first part. This is the second part, and this is the third part. Okay. So this is W1, W2, W3. Okay. So still you see that again the summation of all W should be equal to the total width of the base or the total domain that you are computing the integral, which in this case would be 2, right? So for 3 sampling points, you see that if you sum this up, right? So you get exactly 2. Okay. All right. So this is the concept of numerical integration in 1 dimension. Now, what about the concept of numerical integration in 2 dimensions? Okay. You can take a look at this picture right here. Okay. So suppose you are trying to compute this integral right here. Okay. So again, we're gonna be looking at the integral in each direction, x and y, right? So you can think of it as now having having sampling points in each direction. Okay. For example, if you have only 1 sampling point, the sampling points would be in the middle right here. Okay. So what you need to do is you just need to find the value of the function at this point right here, which would be 0, 0. Okay. And now you use this value of the function to multiply with what? Because we've talked about this before. When you are computing this integral of a certain function over an area, right? What you are basically computing is you computing the volume, right, of this prism right here that comes from projecting this function onto this area, right? So what you are computing is you are computing this volume of this prism. Okay, right here. So if this is what you are computing, so when you use numerical integration, what you need to do once you obtain your sampling points, okay, for example, in this case, you already have sampling points here. So what you need to do is you use this sampling points as the representative value and then multiply with the area of the base, right? So you multiply with this area right here, okay, to get the approximate integral. Okay. And how you obtain the area? You obtain it from multiplying this width right here in x direction with this width right here in y direction. Okay, so what you are having is essentially this representative value of the sampling point at the sampling points multiplied with wx and then wy, which is the area of the base, right? Okay. Now, if you have more than 1 sampling points, for example, if you have 2 sampling points in each direction, okay, so what does it mean then? So if I have 2 sampling points in each direction, it means that now suppose my sampling point is right here, okay. So in X direction, I have two sampling points. In Y direction, okay, I also have two sampling points here. Okay, so two in X direction and two in Y direction. Okay. So I would now have four representative value of my function, right, at these sampling points. Okay, and what I need to do is I need to compute the volume of the prism, right, by using this representative value of my function. Okay, but now since you have 4 points, so you can think of it as you are dividing or subdividing your prism into 4 quarters, right? So you would have a prism coming from this quarter right here, okay, and you use this representative value to compute the volume of this prism within this quarter. Okay. Now you have another quarter here, all right, and you have this quarter here and this one. Okay. So suppose this location is A, right? Because you have positive direction of X and Y here. Okay. So at this point, I have F, A, right? Now, how do I compute the volume of this prism for this particular quarter? I multiply it with this area, right? With this small area of this quarter, okay? Which would come from this part multiplied with this part, right? Okay. So this would be my W X, W Y, okay, for this quarter, right? Which in this case would be equal to 1, right? So this is for 1 quarter. So how do I obtain the volume of the total prism? So I sum this for each of the 4 quarters together, right? Okay. So that's what this equation is telling you, okay? So depending on the number of sampling points in each direction, this is the number of sampling points. For example, if you have 2 points, okay, so you have 2 in X direction and 2 in Y direction. So you have a total of 4 sampling points, right? Or sometimes we refer to it as a 2 by 2 point. Okay, so 2 in each direction. So a total of 4. So what you need to do is you compute this volume of the prism for each of the sampling points, right? So for each of the sampling points, you compute this term, okay? So it means that you would now have a total of 4 of these terms, okay, to sum together to obtain the approximate integral. Okay. All right. Now, for a 3-dimensional case, it would look a bit more complicated because you can think of it in terms of 3-dimensional physical computation of volume, okay? But still the same concept applies. If you have a 3-dimensional space, okay, So suppose you have 2 points in each direction. Okay. So in X, in Y, and in Z. Oh, I'm sorry. X here, Y here, Z here. Okay, to follow the right-hand rule. So in each direction, you can have 2 points, right? So in X and in Y, you would have 4 points right here. Okay. But now in Z direction, you would have another 2 points. So you would now have uh, 2 by 2 by 2, right? 2 points in each direction. So you would have a total of 8 points. Okay, so 8 points, 1, 2, 3, 4, 5, 6, 7, 8, like this. Okay. So what you need to do is, again, you need to compute your function at the sampling points to be used as your representative value, right? And this, at each of these sampling points, once you obtain the value of your function right here, you multiply it with the weight, okay, with the weight factor, okay, which will be this factor right here, okay. Now the weight would include 3 terms now because you have weight in X direction, in Y direction, and in Z direction. But in this case, you can't think of the multiplication of all these weights to be, you know, the area or the volume or something, because you can no longer visualize it as computing the volume resulting from projection of the function in 3 dimensions. Okay? But you can compute this weight multiply with this function at the sampling point, okay, to obtain this term for one sampling point. And you do the same thing for each of the sampling points. So basically, you are computing this term for each sampling point. So in this case, you have a total of 8 sampling points. So you would have 8 of this term for each sampling point, okay? So, and then in the end, you just sum them up together to obtain your approximate integral. Okay. So this is the concept of numerical integration. So we're going to be using this to compute or to obtain our element stiffness matrix instead of doing or computing the integral analytically. Okay. All right. So now the remaining question is, how many sampling points do we need? Okay. As we mentioned before, if you use n sampling points, you can exactly integrate polynomials of order 2n minus 1, right? So if you know the order of your the order of polynomials that can use to represent your function, then you should be able to determine how many sampling points. Okay. So we're going to take a look at the order of polynomials for our function. Okay. So the function that we are essentially computing the integral is this function right here. Okay. Because we are computing the element stiffness matrix, right? Now we need to see what's the order of polynomial resulting from this multiplication of the B matrix with this of this term. Okay. So if you look inside the B matrix, you know that the B matrix contains the derivative of the shape functions like this. Okay. Now, besides the B matrix, you also have this determinant of the Jacobian matrix as well. Okay. So the determinant of the Jacobian matrix would contain terms like this. Okay. Because we have seen that the Jacobian matrix looks like this, right? Okay. And also for the B matrix itself, we know that the B matrix contains the derivative of the shape function with respect to x and y, right? But in parametric coordinates, we change the B matrix from a function of x and y to a function of c and eta. So instead of writing the derivative of the shape function with respect to x and y, we change it to c and eta, right? So we need to look at this term in terms of c and eta. And previously, we have seen that the derivative of the shape function with respect to x can be written according to this equation right here. Okay, so you see that it consists of the J star term, which is the inverse of the Jacobian matrix, right? Which is also multiplied with the derivative of the shape function with respect to c and with respect to eta. So you see that this term is essentially a function of c and eta of different orders. Okay, because this J star is the inverse of the Jacobian matrix. So in computing the inverse, you see that you would have the determinant term as your denominator, right? So this determinant becomes your denominator inside the J star or the inverse of the Jacobian matrix. Okay, so now if you look at each of these terms and you try to come up with the order of polynomials that the final term would end up with, you would see that each of the thickness term would be computed based on this. Okay, so in the end you would have something like this, and each of this term is alpha term would have c eta and c eta term, and each of these term would also have c eta and c eta term. So meaning that this term and this term would end up with this second order terms of c and eta. Okay. So the question remains with this term right here, the determinant of the Jacobian matrix. Now, if this determinant is constant, then all this term would end up with this order right here. Okay. But if this is not constant, meaning that the Jacobian can be this function right here. So you would end up with a polynomial as your numerator and also another polynomial as your denominator, right? So in this case, the order of polynomial would be complicated. Okay, it wouldn't be this second order. You would end up with second order only for j being constant. Okay. So you have two separate cases, one in which j is constant. Okay, so if j is constant, you have a second order polynomial, so you should be able to use a 2x2 rule to exactly integrate your element stiffness matrix, right? But if j is no longer constant, then you would end up with this case where you have one polynomial divided by another polynomial. So in this case, the 2x2 rule would only provide approximation for your element stiffness matrix. And again, when do we have j being constant? The determinant of the Jacobian matrix would be constant over our element if the shape of your element is either a rectangle, right, or a parallelogram. Okay, so if the shape of your element is a parallelogram or a rectangle, then you would have j equal to constant. All right, but in other cases, your j would not be constant. Okay, so now in practice, they are going to call full integration, okay, that the number of sampling points that can exactly integrate your element stiffness matrix for the case with j being constant. Okay, so in the first case, okay, the first case where j is being constant for a rectangular shape or a parallelogram shape of your element, if you can use this number of sampling points to exactly integrate your element stiffness matrix, then this is called full integration order. Okay, so the example of full integration order for different types of elements are shown here. Okay, so for 4-node element, okay, the full integration order is 2x2. So it means that you can use 2x2 points rule to exactly integrate the element stiffness matrix if j is constant. Okay. Same thing here for 8-node element. You can use 3x3 points. So if you use a 3x3 points, the total sampling points would be 9, right? So you would have something like this as your sampling points. So a total of 9 points. Okay. Same thing for 9-node. Okay, 3x3 points would be your full integration order. Okay. So this is the full integration order, or the order of integration, or the number of sampling points which you can use to exactly integrate the element stiffness matrix in case where j is constant. Now, in practice, you would see that even though you know that full integration order would give you the exact integral for your element stiffness matrix, but people most of the time would not prefer using full integration order. Why is that? Why is that? Okay. People would like to use full integration order, but they would prefer using what we call reduced integration. For example, instead of using 3x3 points for 8 node elements, people would use, or people would prefer using 2x2 points. The question is, why is that? Okay. So first of all, in terms of computation expense, right? If you use a 2x2 instead of 3x3, it means you are computing multiplication at 4 points instead of 9 points. Okay, so you are doing multiplication 4 times instead of 9 times, right? So basically, you are reducing the cost of your computation quite a bit. But besides, saving some cost, would it also provide better solution as well? Okay. Now, as you can see, if you use lower number of sampling points, right? It means that you are essentially under integrates the higher order terms. So what would result is the stiffness terms that you obtain would become smaller. And what would happen if you get a smaller stiffness term? It means your structure becomes less stiff, right? So your structure becomes less stiff or more flexible, okay? Which, if you think back to what we have discussed on the issue of energy concept, right? We talk about in most finite element problem, you would see that the stiffness matrix that you obtain from a finite element model is too stiff. Okay. So if you obtain a less stiff structure, okay, you would get a better solution, or you would get closer to the exact solution. All right. So this comes from using reduced order, reduced integration. But the question is, if it's better to reduce the order of integration, why not using, a 1-point rule? That's the minimum order possible, right? So you can just use 1 point for your sampling point then. Okay. It's leads us to this question: what is the minimum integration order we can use? Okay, so the order of integration is still limited by this right here. Okay, because you are still computing the element stiffness matrix, right? So you need to be able to somehow capture certain behavior of the structure. For example, the constant strain state or the constant stress state, right? Because we have seen before that we need to be able to use our finite element model or our finite element to represent the constant strain state. Okay. So in this state, if you take a look at the strain energy, you will see that in order to compute the strain energy based on the constant strain state and constant stress, you see that you need to be able to compute this, right? Okay, because if this is constant and this is constant, when you're computing the integral, you just pull these terms away from the integral. Okay, so basically you are left with computing the volume of the element. So the minimum order of integration is the order in which you can still obtain, or you can still exactly integrate the volume of the element. Okay. Which is this term right here, in this case. So if you take a look at, again, the determinant of the Jacobian matrix, right? You see that the determinant of the Jacobian matrix would have this term right here. Okay. So in order to be able to exactly integrate this, you need a certain sampling points, a certain number of sampling points to do so. Okay. So you see that, for example, for a 4-node element, the reduced integration would be 1. Okay. For 8-node elements, the reduced integration would be 2 by 2. For 9-node elements, the reduced integration would also be 2 by 2. Okay. So this is the reduced order of integration that can be used to exactly integrate the volume of the element. Okay. Now, we have full integration order and we have reduced integration order. The question is, which one should we use for each type of element? Okay. Now this comes from experience. If you use different types of elements to try to solve your finite element problems a couple of times, then you will see that certain types of elements work well with certain number of sampling points. Okay, so that's why we have this third column right here, which is the recommended order of integration order to be used for each type of element. Okay, so for 4-node element, even though you can use a reduced order of integration of 1 sampling point, but the recommended order would still be a 2 by 2. Okay. For 8 nodes, okay, the reduced integration order is 2 by 2, and you will see that the recommended order would also be 2 by 2 in this case. Okay. For 9 nodes, the reduced order is 2 by 2, and the recommended order would be 2 by 2 for a case where you have J being constant, but for J not being constant, a 3 by 3 point is recommended. Okay. So you see that different sampling points would be recommended for different types of cases by using different types of elements. Okay. Now, for this 4-node element, for example, why do we prefer using a 2 by 2 instead of a 1-point rule? Okay. Okay, let's The answer would come from looking at different modes of deformation for your elements. Okay. Now you see that if you look at this deformation modes for a rectangular element, okay, the first three modes here, this 1, 2, and 3, these are rigid body movement, right? So under this rigid body movement, it means the strain is 0 everywhere within your element. Okay, so either you use a 1-point rule or 2-point rule, doesn't make any difference because at any point within your element, the strain will be 0. So when you compute your element strain based on these sampling points, right, you will get 0 anyway. All right. What about number 4? Number 4 here. If you look at number 4, you see that in this case you have simple expansion in both directions, right? So if you use 1-point rule, then the strain at this point would be non-zero, right? Because you at this point you see that you have extension in both directions. Or if you use 2 points, 2 by 2 points, at this point you see that the strain are also non-zero, right? Okay. So in this fourth mode of deformation, either you use 1-point rule or 2-point rules, the strain are non-zero. Okay. Now, what about this fifth mode? Okay. If you use 1-point rule, then you see that strain are also non-zero, right? In this direction and this direction. Okay. Same thing, if you use 2-point rule, you would also have non-zero strain at this point. Okay. What about the sixth mode? Okay. You also have non-zero strains both for 1 point and 2 points, right? For the sixth mode. Now, for 7th mode, what happens if you use 1-point? You see that under this deformation shape, the strain here is 0, right? Because there's no deformation in this particular location right here. Also, if you look at this particular location, there's no strain at that particular location in x direction as well. So it means that in this case, if you use 1-point rule, then you get zero strain, right? Now, what if I change to 2 points? Yeah. I use 2 by 2 points. So I see that even though in y direction the strain is 0 in y direction, right? But in x direction, you will see that the strain is non-zero. Okay, in x direction. So by using 2 by 2 points, the strain components become non-zero. Okay. Same thing for the eighth mode. Just change the direction a little bit. Okay. So you can see that if you use 1-point rule, okay, you would have these two modes of deformation that would give you 0 strain and 0 strain energy. Okay. So these two modes are called 0 energy modes. Okay. Which essentially should not be 0 because you can see that the strains are non-zero, right? And you see some deformation going on. So the total strain shouldn't be 0. But if you use a 1-point rule, the strain would appear to be 0, as well as the strain energy. Okay, so that's why in most cases, because you can have additional 0 energy modes from using 1-point rule. So that's why we would tend to avoid using a 1-point rule. Okay, so we just stick with the 2 by 2 point for 4 node elements, even though the reduced order of integration is 1 point. All right. Okay. Now, this is another example of an 8 node element. Okay, and 8 node elements, you can also have this 0 energy mode as well if you use a 2 by 2 point rule, but still okay. So if you use a 2 by 2 point rule here, then you see that at this particular location here, the strain is 0, right? So that's why if you use this point to compute the representative value of your function, which contains the b function, right? The b function tells you the strain component. Okay, so if you use these points, you see that the strain at this particular location would be 0. Okay. But even though we have this case for using 2 by 2 points for 8 node elements, people will still prefer using 2 by 2 point rule. But what they have to do is they have to try to avoid having this kind of deformation inside your finite element model. Okay. So you can avoid this by choosing proper aspect ratio for your element. Okay. So the height and the width of the element, if you select it properly, then you can avoid having each element going through deformation like this. All right. So that means that when you perform the finite element computation, instead of computing your element stiffness matrix by using analytical integration, you're going to use numerical integration instead. So by using numerical integration, what you need to do is you compute this term, each of the element stiffness matrix term based on this okay, based on this kind of equation. Okay. All right. So basically, you are computing the multiplication of different metrics, right? And each of these metrics, right, the B matrix, needs to be evaluated only at the sampling point based on our numerical integration scheme, right? So because you know that each term inside B can be written as function of C and eta, right? So you just plug in the sampling point here in order to compute this B, okay? So you will get this term at for each of the sampling point, okay? So also the Jacobian matrix, okay? The determinant of Jacobian matrix needs to be evaluated only at the sampling point, okay? So basically you are doing the computation within each element only at the sampling point, right? And you do it for the total number of sampling points. For example, if you have a 2x2 point, so you do this computation 4 times, right? Okay. So you do this computation 4 times, and then you obtain the element stiffness matrix. Okay. So because we are computing everything at the sampling point, the B matrix is computed at the sampling point. So in a way, you are evaluating your element stiffness matrix based on what's going on at the sampling point. Okay, and remember that the element stiffness matrix comes from the product between strains and stress, right? Or to be exact, stress and virtual strain, right? Because it represents the internal virtual work term. And the stress comes from strain, okay? So basically, if you think about it, because you are evaluating everything at the sampling point, you obtain the element stiffness matrix also at the sampling point. So the strain values at the sampling points should be the most accurate value of your strain, right? So within an element, if you want to choose the value of strain to be the representative value for your element, then you would prefer choosing the value of strain at the sampling point because you are computing the B matrix at the sampling point. Okay. But in most cases, or in some case, you may want to use the strain values at other points within your elements as well, besides at the sampling point. For example, we talk about using strain jumps across element boundaries as a measure of error for your final element solution, right? So you need to compare between different elements, whether you know, if you move across the element boundaries, how much is the strain jumps across element boundaries? So in those cases, you need to compare the value of strain at the nodes, right? Which defines the boundary between elements. So how can we compute the value of strain at the nodes then? Because we're computing everything at the sampling points, So what you can do is you can, one way to do it is you can extrapolate. Okay, you can use this extrapolation of your stress or strain value from the sampling point to the nodes. Okay, and the extrapolation function that you're going to use to do this computation is the same function that you use to interpolate what's going on inside your element. Okay, so before we have the interpolation function, right, to interpolate everything inside our element based on the nodal quantities. Now you have the quantities at the sampling points, but you want to extrapolate those quantities to the nodes. Okay, so we're going to be using the same function to do this extrapolation. Okay, so we're gonna do something like this. Okay, so you're gonna think of having another coordinate system, which is basically, you know, pretty much the same as your parametric coordinate system, right? But now you're going to call it an R and S. Okay. So we're gonna try to expand from this sampling points right here, okay, to this node right here, or you just kind of extend this value to this value, right, and extend this value to this value, right? Okay, so that's what we're trying to do. Okay, so you can, because R and Z pretty much align with each other, right? You just kind of scale them up. Okay, so you scale from this location to this location. Okay, so you can think of R is equal to C multiplied with square root 3, right? Just try to scale them up a little bit. Okay, and S as the equals to eta times square root 3. Okay, so basically you can write the extrapolation function by using this same format as for C and eta, right? But you can just write it in terms of R and S, okay? Because the relationship between R and C is just scaling by a constant, okay? The same for S and eta, you're scaling S up by a certain constant. So you can use the same format of the interpolation function in terms of C and eta, but write it in terms of R and S instead. Okay. So if you substitute R and S as square root 3 and square root 3, then you can get the value of your strain at the nodes. Okay. So you can use this simple form of extrapolation function to compute the strain at the nodes, instead of having to, compute the B matrix again at the nodes. Okay. Otherwise, once you obtain the nodal, for example, you obtain the nodal displacement. Okay. If you would like to compute strain, normally you would have to compute the B matrix multiplied with the nodal displacement, right? Okay. So, for example, if you want to compute strain here, then again you must compute the B matrix at the node, which would, take too much computational effort to do so. Instead, you can just use once you obtain the strain values here, okay, at the sampling points, you can use this B matrix that you have evaluated at the sampling points, okay, because you need them to compute or evaluate the element stiffness matrix. So you can use them and extrapolate to the nodes, okay, instead of having to compute the B matrix all over again. Okay. So this is the concept of extrapolation of the strain values based on, kind of scaling the parametric coordinates a little bit. Okay. All right. Now, by looking at the parametric coordinates, okay, so you see that you can also use parametric coordinates to map between elements with complicated shapes in Cartesian coordinates to a very nice and easy shape in parametric coordinates as well. Okay, and still you would be able to compute the element stiffness matrix. For example, you can also map what we call higher order elements. Okay, higher order elements mean the order of polynomials that you can use to approximate the quantities inside the elements can be higher than the linear function. Okay. For example, if you go up from one order up from a linear function, you get a quadratic function, right? Now, if you go even higher, then you get a cubic function, something like that. Okay. So from linear to quadratic to cubic, what's the difference between these elements? We've seen before that for elements with linear approximation, right? For example, for 4-node elements, the shape of the element or the edge of the elements, if you look at its deformed shape, it must remain linear, right? Even though it can change in length or the angles between two edges can change, but still the edge of the element must remain linear. Okay, that's the constraint of the 4-node element. But what if you use higher order elements? Okay, for example, if you put more nodes onto each edge of the element like this, then it means that now you can have quadratic function, right, along each of these edge. So when it deforms, when this element deforms, it can have curved edge like this now. Okay, If you have two nodes on each side, then you can only have linear deformation. But now, once you put three nodes on each side, now you can have curve deformation going on each side like this. Okay, so you can have curve like this on each side of the element. So this is somehow referred to as curved element. Okay, so you can have linear elements and curved elements. Okay, all right. So if you look at this type of element, for example, we look at the second order element or quadratic elements. The quadratic elements would have 8 nodes like this. Okay. So you see that in the Cartesian coordinate system, the element can have curved edge. Okay. So how can we compute the element stiffness matrix if you have the domain of the element to compute like this? You have a curved domain like this. It would be difficult, very difficult, right, to compute an integral over this type of domain. So we're gonna make use again of the parametric coordinate system. Okay, so you're gonna map from this curve element to a nice and easy square like this. So still you're gonna have C from -1 to 1 and eta from -1 to 1 like this. Okay, and we're gonna number the nodes of the element like this: 1, 2, 3, 4. Okay, and then 5, 6, 7, 8 like this. Okay. So for higher order elements, how do we obtain the shape functions for this element? Okay. Now the easiest way that you can obtain the shape function for this element is by decomposing the shape function into, a number of different functions. Okay. In this case, we're gonna decompose our shape function into 2 separate functions multiplying with each other. Okay. The first part, or the f function would make the shape function follow a certain property. Okay, and the g function would also make our shape function follow another property. Okay, now the first property that the f function would make is it makes the shape function equal to 0 at specific nodes or along specific edges. Okay, for example, we know that n1 must be 0 at all the other nodes, right, beside node 1. Okay, so this is what the f function would do. Okay, what about the g function? The g function would be the part which would give you the correct powers of c and eta. Okay, and in this case, because you have 3 nodes on each side of the element, so the shape function should be in quadratic form. Okay, so once you obtain the f function, you just put the g function to give the correct power of c and eta for the shape function. Okay, let's take a look at an example then. If we take a look at N1. Okay, N1 should vanish. Okay, N1 is shape function for node 1, right? So the shape function for node 1 should be 0 here and here. Okay. So how do you make it 0 along the entire edge 4, 7, and 3? Along this edge is the edge where you have eta equals to 1, right? So to make N1 equal to 0 along this edge, you need this term right here. Okay, because if you plug in eta equals to 1, this would give you 0. Okay. What about this edge right here? This is the edge where C equals 1, right? So in order to make N1 equal to 0 along this edge, you need this term right here. So if you have these two terms together to make N1 equal to 0 along this edge, eta equals to 1, and this edge where C is equal to 1. So the first part or the F part should contain this, right? Would make N1 vanish along this edge. Okay. Now we already have this part on this part. Now we need this part right here. Okay. This is the part where you need to have a correct order of polynomials for N1. Okay, and N1 should be in quadratic form. Okay, so you need to have this form of function g. Okay. And based on this form, you want to solve for this coefficients C1, C2, and C3. So we can do that by enforcing these conditions onto N1, right? So you know that N1 is equal to 1 at node 1. Okay, so at node 1 or at this value of C and eta, N1 is equal to 1. And we still have information at node 5 and node 7, node 8, which have not been used. So we're going to use the information at these two nodes. Okay, at node 5, you see that. Okay, N1 is also 0 here. Okay, and at node 8, you also see that N1 is equal to 0 as well. So you use these three conditions to solve for C1, C2, and C3. So you will see that you would get N1 that looks like this. Okay. So this is how you arrive at the shape function for this 8-node element. Okay, so you can do this for N1, N2, N3, N4, and then repeat it again for N5, N6, N7, N8. Okay, so you would have something like this in the end. Okay, so all the shape functions would look like this. Now, once you have these shape functions, okay, you can follow pretty much the same procedure for computing, all other quantities of interest. For example, you can use this n to approximate the displacement function within your element based on the nodal displacement, right? You can also compute the B matrix, okay? And the B matrix would be derivative of this shape function with respect to x and with respect to y. Okay. You can also write the B matrix in terms of C and eta as well. Okay. All right. Or you can follow pretty much the same procedure that we have done before for 4-node elements. Okay. Now we're going to be looking at a specific quantity of interest, which is the element loads. Okay. Again, we have performed computation for equivalent element loads before, right? If you can still recall, we use the concept of work equivalent element loads. Okay. So what did we do in computing the element loads? We start with the virtual work equation, right? We look at each term inside our virtual work equation, and we see that the external virtual work computed from the element loads. Okay, in this case, we start by looking at the body force. So the virtual work computed based on the body force is this term right here. Okay, now what we need is we try to convert this term into this term right here. Okay, because we need this equivalent body force that is associated with the nodal displacement or the nodal degree of freedom, right? If we have this equivalent body force, then we can find the contribution of this equivalent body force to the load vector that acts at each degree of freedom of our finite element model. Okay. All right. So we're going to use pretty much the same concept that we have done before. Okay. So you have seen that this part, okay, can be approximated by using the finite element approximation scheme, which is this scheme right here. So we can approximate the virtual displacement field by using the shape function multiplied with the virtual nodal displacements. Okay. So if you do that, then it means you can have or convert this as del u at transpose multiplied with this and transpose times b. Okay. So this part just comes from this approximation right here. Okay. Okay. So you see that this essentially represents this work equivalent body force. So I mentioned previously that in case where you happen to know the function of this body force, you can just plug this in to obtain the necessary equivalent body force, right? Okay. So for example, if you have, okay, let's say we can look at a simple example of a one-dimensional problems like this. Okay, let me okay, suppose this is x equals 0. Something like this, and we have a body force that looks roughly something like this. So this is let's call this B0 then. Okay. And the body force here is zero. Okay. Okay, let's call this node 1, 2, 3. 1, 2, 3. Yes. Okay, so for example, if I want to compute an equivalent body force at node 1, at this node right here. Okay. Now, in this case, I know exactly how the body force looks like, right? So I know the distribution of the body force. So I can perform this computation either in parametric coordinates or in Cartesian coordinate system. Okay. So what I need is I need to know the shape function, right? That is associated with node 1 because I'm computing the equivalent body force at node 1. So what I need is, okay, N1 in this case. So for okay, so N1 this case takes its form. Okay, let's check if this N1 is equal to 1 at node 1, right? At node 1, you start in -1. Okay, so this would give you what? My 1/2 plus 1/2, which is 1, right? And on the other nodes, N1 is equal to 0, right? Okay. So this is my N1 in terms of parametric coordinate C. Okay. So I can compute the equivalent force at node 1 by computing the integral, right? From -1 to 1 of N1, okay? Multiply with the body force function, right? The body force function in this case can also be written in terms of C as well, okay? And I also need the Jacobian, right? The Jacobian, which is this right here, okay? Because I'm changing from an integral in Cartesian coordinate system to the parametric coordinate system. Okay. So this is basically what I need. All the information I have would give me the equivalent body force at node 1. Okay. Which is exactly this form. Okay. So you have integral of your shape function, right? The body force function, okay, and then the volume. So I should also have an area right here, okay. So multiply with the area. Suppose the area is constant, okay. So I have constant A in this case. All right. So in this case, you can see that based on this data that we have, dx by dz should be equal to what? We can write a relationship between c and eta like this, right? C equals to x over L. So dx by dc should be L over 2. And this function of the body force, because we have a linear variation like this, so if you write it in terms of the body force function should be zero multiplied with z, right? So this should be the body force function. So the body force is equal to 0 at x equals 0 and equals to be 0 at x equals 1, right? So you can just plug this in. Okay. And then you subtract this into here. And basically what you need is you compute this integral right, to obtain this integral and body force. Okay. So you can try to do this on your own, but the basic idea is if you have this function of the body force, then what you need is just to compute this integral. Okay, and this integral can be done in both parametric coordinates or in Cartesian coordinates. Now, okay, yes, and in this case, because for quadratic elements, okay, it would be a little hard if you do computation in parametric coordinates because the domain would be quite difficult to deal with. So you prefer doing computations in parametric coordinates. Okay. All right. So this is one way to do it. Or we can also approximate the body force. Okay. You can also approximate your body force by using the same shape function or interpolation functions that you use for the displacement as well. Okay, and if you use this approximation scheme for your body force, it means you don't have to care how the body force function looks like. Okay, because you can just know the value of the body force intensity at the nodes. Okay, and you can use those values and approximate the body force within your element by using this approximation function. So in this case, what you would end up with is you would end up with something like this, okay? Which again give you the same form of the Q matrix, right? That we have seen before. So before we have used the Q matrix as well to obtain the work equivalent body force. And you can also do the same thing here for quadratic elements, okay? But now, because you need to compute this in parametric coordinates, so you have to convert it, right, to integral in parametric coordinates. So instead of doing your integral in Cartesian coordinates, you prefer doing it in parametric coordinates because it's a lot easier to do so. Okay. So in this case, you would get Q matrix like this. Okay. And then you can obtain this as your equivalent body force. All right. So this is the example distribution that you would obtain if you have constant body force in x and y direction. Okay, so I think it's time to take a short break here. So are there any questions on what we have discussed so far? So if not, then let me do a quick Thai summary. วันนี้นะครับเราเห็นนะเราเริ่มคุยกันมาตั้งแต่เรื่องของ numerical integration นะครับซึ่งเป็นเรื่องที่เราเคยเรียนมาแล้วนะก็คือเรื่อง Gauss integration นะครับก็Gauss integration เราก็จะมีอะไรฮะเรื่องของGauss point ใช่ไหมหรือว่า sampling point นะครับก็คือเป็นตำแหน่งของจุดที่เราจะใช้ในการเป็นตัวอ้างอิงในการคำนวณค่าต่างๆนะฮะซึ่งจริงๆสิ่งที่เรากำลังสนใจหลักๆตอนนี้นะครับก็คือไอ้ตัว stiffness matrix ใช่ไหมฮะที่เราจะต้องคำนวณนะครับแต่จริงๆนอกเหนือจาก stiffness matrix นะคุณก็จะเห็นว่ามันมีค่าอื่นที่เราต้องคำนวณด้วยใช่ไหมฮะเช่นอย่างเมื่อสักครู่เราพูดถึงเรื่องของค่าแรงใช่ไหมที่เราจะคำนวณออกมาให้อยู่ในรูปของแรงเทียบเท่าที่ degree of freedom ค่าพวกนั้นคุณก็ต้องคำนวณ integrate เหมือนกันใช่ไหมนะครับเพราะฉะนั้นจะคำนวณ integrate ก็แล้วแต่นะครับมันก็เลยมีความจำเป็นที่เราจะต้องพยายามหาโดเมนง่ายๆก็ทำให้เราสามารถที่จะใช้เรื่องของ numerical integration หรือว่า Gauss มาช่วยได้นะครับทีนี้ในการคำนวณของเรานะครับเราก็จะพบว่ามันก็จะมีเรื่องของตำแหน่งของ sampling point ใช่ไหมที่เราจะเลือกใช้จำนวน sampling point นะครับที่จะเลือกใช้แล้วก็ค่า weight ใช่ไหมที่จะต้องไปคูณกับไอ้ sampling point เหล่านั้นนะครับซึ่งโดยหลักการเนี่ยก็เราก็จะเห็นภาพว่าจริงๆแล้วเนี่ยถ้าเราพยายามเทียบกับเรื่องของการคำนวณพื้นที่ใต้กราฟใช่ไหมในการหา integrate หรือแม้แต่การคำนวณปริมาตรใช่ไหมครับในที่เป็นผลจากการคำนวณ integrate ใน2มิติอย่างเงี้ยมันก็จะทำให้เราเข้าใจเรื่องของการประมาณค่าด้วย numerical integration ได้ดีขึ้นนะครับผมก็เลยพยายามที่จะวาดภาพให้เห็นความเชื่อมโยงตรงนั้นนะครับขึ้นมาซึ่งเราก็จะเห็นว่าในการคำนวณในกรณีของเราเนี่ยเราก็เหมือนกับคำนวณอะไรฮะค่าฟังก์ชันที่เราสนใจที่ตำแหน่ง sampling point ใช่ไหมแล้วก็ไปคูณกับอะไรฮะพื้นที่สี่เหลี่ยมที่เป็นฐานเพื่อที่จะได้ปริมาตรของตัวprism ในแต่ละส่วนออกมานะครับซึ่งอันนี้มันก็จะให้ค่าของการประมาณของการ integrate ออกมาให้เราได้นะซึ่งในวิธีการนี้ก็สามารถที่จะขยายผลไปใน3มิติได้เช่นเดียวกันนะครับซึ่งสุดท้ายแล้วเนี่ยในการคำนวณนะครับเราก็ต้องมาตัดสินใจว่าเราจะเลือกใช้จำนวน sampling point กี่อย่างถึงจะเหมาะสมนะครับซึ่งสุดท้ายก็พบว่าจำนวน order ของ integration ที่นิยมใช้กันเนี่ยนะฮะหรือว่าที่ให้ผลดีสำหรับวิธีการ finite element เนี่ยอาจจะไม่ได้จำเป็นจะต้องเป็น full integration order เสมอไปนะครับตัว full integration order ก็คือจำนวน sampling point ที่ทำให้สามารถที่จะ integrate ตัวค่า stiffness ของเราเนี่ยได้อย่างถูกต้องนะฮะได้อย่างถูกต้อง 100% สำหรับกรณีที่ Jacobian matrix มันเป็นค่าคงที่นะครับซึ่งในหลายๆกรณีก็พบว่ามันไม่จำเป็นต้องใช้ full integration เสมอไปนะครับเราพบว่าสุดท้ายแล้วเนี่ยเราในบางเคสเนี่ยเรา prefer ที่จะใช้เป็น reduced integration นะฮะก็คือแทนที่จะใช้เป็น3 คูณ 3ใช่ไหมอย่างกรณีของชิ้นส่วนที่มี8จุดต่อนะครับเป็น 8 node element เนี่ยแทนที่จะใช้3 คูณ 3ซึ่งเป็น full integration order เนี่ย เขาก็จะนิยมใช้เป็น2 คูณ 2มากกว่านะครับหรือถ้าอย่างเป็นรูปสี่เหลี่ยมเนี่ยนะครับตัว full integration เป็น2 คูณ 2นะฮะจะใช้ reduce เป็นเหลือ1 point เลยจะดีไหมนะครับก็พบว่าก็อาจจะไม่ดีนะในบางกรณีเพราะว่าพอ1 point เนี่ยมันก็จะเกิดปัญหาอื่นตามมานะฮะงั้นจากตรงนี้เองเนี่ยเราก็เลยมาดูว่าอย่างกรณีของชิ้นส่วนที่เป็น4 จุดต่อเนี่ยนะครับมันมีปัญหาอะไรทำไมมันถึงใช้1 point ไม่ได้ใช่ไหมเขาพบว่ามันก็จะมีเรื่องของอะไรฮะเขาเรียกว่าเป็น shape นะครับหรือรูปร่างของ deformation ที่มันทำให้เกิดลักษณะที่เราเรียกว่าเป็นอะไรฮะค่าพลังงานของความเครียดหรือว่า strain energy เนี่ยมันเป็น0นะครับหรือพูดง่ายๆถ้าเกิดคุณใช้ sampling point ไม่พอเนี่ยคุณก็จะพบว่าในรูปร่างเหล่านั้นเนี่ยคุณอาจจะได้ค่า strain energy เป็น0นะทั้งที่จริงๆเนี่ยมันไม่ควรจะเป็น0นะครับยกตัวอย่างก็เช่นกรณีของรูปที่7กับรูปที่8นะซึ่งในรูปที่7กับรูปที่8เนี่ยค่าพลังงานเนื่องจากความเครียดมันไม่ควรจะเป็น0นะครับเพราะว่ามันมีรูปร่างของ deformation เกิดขึ้นชัดเจนนะแต่ว่าถ้าในกรณีนี้เนี่ยคุณไปใช้แค่1 point นะครับเป็นGauss integration แค่1 point เนี่ยคุณจะพบว่าถ้า1 point มันก็จะไปอยู่ตรงกลางพอดีนะซึ่งตำแหน่งตรงกลางเนี่ยถ้าคุณสังเกตดูก็จะพบว่าค่า strain ไม่ว่าจะเป็นทาง x หรือทาง y เนี่ยมันจะเป็น0พอดีเลยนะครับเพราะฉะนั้นเขาเป็นอย่างนั้นก็เท่ากับว่าถ้าเราใช้ 1 point ในกรณีแบบนี้นะครับคุณก็จะได้พลังงานความเครียดที่เป็น0ออกมานะครับซึ่งก็จะผิดพลาดไปนะจากความเป็นจริงเพราะฉะนั้นก็เลยเหตุผลว่าทำไมเราถึงไม่ควรจะใช้1 point นะครับทั้งที่มันสามารถที่จะลดจำนวน integration ลงมาได้1 point ก็ตามสำหรับกรณีของ four node element นะทีนี้จากเรื่องของ Gauss point นะครับหรือว่า sampling point นะครับก็ต่อเนื่องมาก็จะเป็นเรื่องของการคำนวณค่า stress หรือ strain ที่ตำแหน่งอื่นๆที่อยู่ในชิ้นส่วนนะครับถ้าเราสนใจเช่นเราสนใจค่า strain ที่ตำแหน่งโหนดโอเคเดี๋ยวพูดต่อนิดนึงนะครับก็คือเมื่อกี้ค้างไว้ว่าถ้าเราจะคำนวณค่าที่เราสนใจที่ตำแหน่งจุดต่อนะครับก็ได้เหมือนกันแต่ว่าคุณจะต้องไปคำนวณmatrix B ใหม่นะครับที่ตำแหน่งเหล่านั้นซึ่งก็ในการคำนวณ matrix B เนี่ยมันค่อนข้างจะสิ้นเปลืองนะครับการคำนวณพอสมควรทีเดียวเพราะนั้นเราก็เลยมีทางเลือกนะครับว่าแทนที่เราจะทำอย่างนั้นเนี่ยคุณสามารถที่จะใช้การ extrapolate ค่านะครับจากค่า strain ที่เรามีอยู่แล้วนะในชิ้นส่วนก็คือค่า strain ที่ตำแหน่ง Gauss point ใช่ไหมที่ตำแหน่งเหล่านี้คุณคำนวณค่า strain มาอยู่แล้วตอนที่คุณคำนวณB matrix ออกมาใช่ไหมสำหรับคำนวณ element stiffness matrix นะครับก็คือทุกอย่างเราคำนวณที่ Gauss point ไว้อยู่แล้วนะครับ เพราะฉะนั้นคุณสามารถใช้ค่าเหล่านั้นเนี่ยเป็นฐานในการ extrapolate ค่าเพื่อที่จะหาค่าอื่นในชิ้นส่วนได้นะครับที่ตำแหน่งอื่นในชิ้นส่วนได้นะฮะก็เลยใช้คอนเซ็ปต์ของอะไรฮะเรื่องของการ mapping ระหว่าง coordinates คล้ายๆเดิมเนาะแต่ว่าเที่ยวนี้เนี่ย coordinates มันแทบจะซ้อนกันเลยนะฮะก็คือจาก c กับ eta กับอีก coordinates หนึ่งเป็น r กับ s ซึ่งเป็นการเทียบกันเหมือนกับ scale จาก Gauss point ออกมาที่โนดเท่านั้นเองนะครับเพราะนั้นระหว่าง r กับ c กับ s กับ eta เนี่ยก็เลยเหมือนกับเป็นการ scale ค่าออกมานะฮะด้วยค่าคงที่เพราะฉะนั้นเราก็จะใช้ไอ้ scaling เหล่านี้หรือ mapping นี้ในการที่จะคำนวณค่าที่โนดจากค่าที่ Gauss point นะครับทีนี้หลังจากนั้นแล้วเราก็มาคุยกันเรื่องของนะฮะชิ้นส่วนที่ถ้าในกรณีที่เราจะเพิ่มออเดอร์นะครับของ polynomial ที่ใช้ในการประมาณค่านะครับซึ่งก็เท่ากับว่าเราก็ต้องเพิ่มจุดต่อเข้าไปใช่ไหมให้กับชิ้นส่วนของเราซึ่งตัวอย่างที่เราพูดก็คือเป็นเรื่องของชิ้นส่วนประเภท8จุดต่อนะครับ8จุดต่อก็คือเป็นelement ที่เราเรียกว่าเป็น quadratic element เพราะว่าแต่ละด้านก็จะมี3จุดต่อซึ่งทำให้สามารถที่จะประมาณค่าฟังก์ชันในลักษณะที่เป็นกำลังสองได้นะครับเพราะฉะนั้นสำหรับ element หน้าตาแบบนี้นะครับเราก็จะมาดูเรื่องของตัวเชฟฟังก์ชันที่ใช้ในการประมาณค่าต่างๆนะครับในชิ้นส่วนซึ่งเชฟฟังก์ชันก็จะมีลักษณะที่สามารถที่จะเขียนแยกเป็นองค์ประกอบนะครับของฟังก์ชันออกมาได้2ส่วนใช่ไหมซึ่งก็ทำให้เราสามารถที่จะ derive เรื่องของเชฟฟังก์ชันได้ง่ายขึ้นนะฮะก็จะเห็นว่าหน้าตาเชฟฟังก์ชัน n1 ไปจนกระทั่งถึง n8 ก็จะมีหน้าตาที่แตกต่างกันไปแต่ว่าที่สำคัญก็คือตัว properties ในลักษณะเดิมยังอยู่นะฮะก็คือว่าค่าเชฟฟังก์ชันที่ตัว n1 ก็ต้องเท่ากับ1ที่โหนด1ใช่ไหมแล้วก็เท่ากับ0ที่โหนดนะครับดังนั้นproperties นี้ก็ยังเป็น properties สำคัญจากนั้นเราลองมาดูว่าสำหรับไอ้เจ้าquadratic element เหล่านี้เนี่ยนะครับถ้าเกิดเราจะคำนวณเรื่องของตัว work equivalent force นะครับเราจะทำอย่างไรก็จริงๆแล้วคอนเซ็ปต์ก็จะเหมือนกับที่เราเคยทำสำหรับกรณีของชิ้นส่วนที่เป็นโฟโนดเหมือนกันเลยนะครับเพียงแต่ว่าเรื่องนี้การอินทิเกรตมันก็ถ้าเราทำในตัว parametric coordinate ก็อาจจะง่ายกว่าเนาะเพราะว่าตัวชิ้นส่วนของเราเนี่ยมันเป็น curve element ไปแล้วนะครับเพราะฉะนั้นถ้าเป็น curve element เนี่ยคุณจะไป integrate ในพื้นที่ของเจ้า curve element มันก็คงเป็นไปได้ลำบากเพราะฉะนั้นเราก็เลือกที่จะไป integrate ใน parametric coordinate จะดีกว่านะครับก็ยกตัวอย่างให้ดูนะครับสำหรับชิ้นส่วนที่อยู่ใน1 มิตินะครับ1 มิติง่ายๆก็เราก็สามารถที่คำนวณในตัวพวก work equivalent เนี่ยออกมาได้นะฮะ work equivalent body force นะก็จะมีค่าตัวอย่างนะครับของการกระจายค่า work equivalent body force มาให้อยู่สำหรับชิ้นส่วนที่เป็นประเภทต่างๆนะครับก็เดี๋ยวเราก็จะมาคุยกันว่าหลังจาก body force แล้วสมมติกรณีที่เป็น traction บ้างนะครับ traction แล้วเราจะพิจารณาอย่างไรนะครับก็ไม่ทราบมีใครมีคำถามไหมOkay, so if there are no questions for a body force, now let's take a look at the surface traction. Okay, so in this first case, suppose we have a surface traction acting in only one direction. So we have surface traction acting only in y direction in this example. Okay. So you have this different traction intensity in y direction at along this edge. for 7 and 3 of this particular element. Okay, so how can we compute the work equivalent traction at each node along this edge then? Now, in this case, you see that cause traction is acting only in one direction when you compute the virtual work, right? So the virtual work would result only from the virtual displacement in y direction, which is delta v. Okay? So you have no external virtual work resulting from delta u because there is no force acting in x direction, only in y direction. Okay. Now the complicated thing about this problem is how can we compute this integral along the curve edge, because this edge 473 is a curve. So that means in order to compute integral along this edge, you need to be able to compute a curve integral. Okay. So how can we do that? So start by looking at looking along this edge 473. Okay. So along this edge, one thing that we do know is if you map this back to the parametric coordinate system, you will see that on edge 4, 7, and 3, if you look at the mapping, on this edge 4, 7, and 3, eta is constant, right? So on this edge, you have a constant eta equals to 1. So you can think of it as only varying in z direction, okay, with a constant eta. So in parametric coordinates, eta is equal to 1. Okay, and c is varying from -1 to 1. All right. So we would like to somehow be able to map between the contour along this curve edge. Let's call this S, curve S. Okay. So we want to somehow map between S and eta. Okay. So you can write now S as a function of and C, I'm sorry, as a function of C, because eta is constant on this curve S. So along this edge, okay, the displacement or the virtual displacement V, okay, can be approximated by using this finite element approximation scheme. So you see that we only have N4, N7, and N3 involved because all the other N's are 0 along this edge, right? Only the N's associated with the nodes on this edge would be non-zero. Otherwise, it would be 0. Okay, and you can plug in the value of for this N by having a constant eta equals 1. Right, so let's call the value of N4 with eta equals 1 by using the symbols right here. Okay. So we do the same thing for N7 and N3. So we have this bar representing the shape functions evaluated at eta equals 1. So you can plug this back in to your virtual work equation. Okay, so you approximate your virtual displacement by using the shape functions in bar, okay, at node 4, 7, and 3. And then you have this traction acting in y direction. So again, if you happen to have this traction, if you happen to know the certain function representing this traction in y direction, you can just plug this in to this equation right here. But in case where you don't want to worry about, the variation of traction along the edge, you can just approximate this variation by using the shape function as well. So if you use the shape function to approximate your traction, then again, you can use the same set of shape function to approximate this traction acting in y direction. And you can approximate that based on the traction intensity at each node. All right, so if we do that, then again, you would have something like this, okay? So you would have something like the Q matrix again, right? But this Q matrix now would involve only node 4, 7, and 3. So the Q matrix would be a 3 by 3 matrix in this case. So you have something like this. Now, the only remaining question is how can you evaluate this Q matrix based on this contour integral or curve integral ds, right? So in order to do so, you need to be able to somehow write S or ds in terms of z and dc, right? Okay, so by using this relationship right here, normally for any curve in Cartesian coordinate system, we can somehow find this relationship. We can think of ds as this. You approximate this ds by a segment, right? Based on dx and dy, like this. Okay. So this vector ds, okay, can be approximated as dx I plus dy t. Okay, something like this. Okay, so if you want to compute the magnitude of this ds, then you can do so by based on this dx component and dy component. So you get something like this for the magnitude of ds. All right. Now, with this relationship between ds and dx dy, you can approximate your dx and dy by the parametric coordinates that we have previously, right? So previously, you can approximate dx and dy in terms of dc and dA, right? Okay, so you can use this relationship, okay, to plug back into this relationship in order to find the relationship between ds and dc. Okay. Now in this case, the eta would be 0, right? Because you have eta being constant and eta equals to 1. Okay. So based on this constant eta equals to 1, okay, you will see that in the end, if you plug everything back into the equation, you would get something like this, okay? So you have this relationship between ds and dc, like this. And again, this J11 and J12 just represent the Jacobian matrix, right? So with this relationship, okay, in the end, what you need to do is just plug this back into the integral here. So you would see that now instead of computing this integral on ds, you can write it in terms of an integral in parametric coordinates, okay, which is dz, which is a lot easier to compute because now the domain in dz would be from -1 to 1. Okay. So you can evaluate this integral right here to obtain the work equivalent traction acting in y direction. Okay. Now, in evaluating this integral, again, because you would have a simple domain to deal with, so you can also apply a numerical integration scheme to compute this integral as well. Okay, so you don't need to compute the integral analytically. You just need to do it numerically. All right, so you can, in the end, find the work equivalent traction, okay, that would act each node. So this example of the distribution of the traction on the edge for constant mission. Now, in this case, you have traction acting only in one direction. Okay. If you have traction acting differently in different directions, how would we manage to compute the work equivalent force then? For example, you can have what we call the pressure load, right? What is a pressure load? The pressure load is the load with the direction of the load acting normal to the surface. Okay. So on a curved edge, if the load is normal to the surface, then it means that the direction of the load keeps changing, right? So how do we deal with this kind of loading then? Okay. Because you can have normal vector pointing in different direction along the curved edge, right? So you need to be able to write this normal vector. Okay. So how can we obtain this normal vector to the curved edge? Okay. So if you look back at this curve, okay. Now suppose we want to write a normal vector here to the curve, to this curve right here. What we can do is first we can try to find a tangent vector to this curve, right? So the tangent vector to this curve, because ds is a function of c, so the tangent vector would be what? Would be ds by dc, right? So this would give you the tangent vector of the curved edge when you move along in z direction. Okay. So we need to compute the slope or we need to compute this tangent first. And once you can find this tangent vector, how do you compute the normal vector? So you think about it, a normal vector can probably be obtained by, because you know that if you look on a plane, you have the axis C pointing out of the paper, right? So if you have a unit normal vector K to point in the direction of Z axis, once you obtain this tangent vector, you can cross K with this tangent vector, right, to obtain the normal vector. So this normal vector can be obtained by crossing your K with this tangent vector, okay? Let's call this a V1 vector. So if you cross this unit normal vector K with V1, then you can obtain this normal vector, okay? All right. So we're gonna try to do this, okay, to obtain our normal vector along the curve S. Okay. So based on this tangent vector, okay, you know that you can write ds in this form. So you can write ds in the form of vector as well. So we can construct the tangent vector v1. Okay. This is our tangent vector here. So we can gonna construct our tangent vector based on ds, okay, ds by dc. Okay. So we get this vector right here for your tangent vector. Okay. So again, this is j11, this is j12. So you have this relationship here. So v1 is the tangent vector to theta equal constant lines. Right. Now the normal vector can be obtained from crossing K with V1. Okay. And if you convert this to a unit normal vector, unit vector, so just because K is already a unit vector, so you can just divide it by the magnitude of V1. Okay. All right. So you can see that the product, the cross product between K and V1 will give you this vector right here. So the unit normal vector can be written as this vector right here. Okay. So you see that the unit normal vector will keep changing, okay, along the curve S with respect to all these Jacobian components. Okay. So once you have this unit normal vector n, what you can do is you can convert this pressure load to the P acting in y direction and P acting in x direction, right? How do you do that? If you have the unit normal vector, right? If you write this in terms of x component and y component, then if you want the x component of pressure load, you can just, this is your in matrix, right? unit normal vector. So the pressure load can be written as P n F like this. Okay. So if you want Px, you just dot your P and F, the unit vector in x direction or the unit vector I, right? So if you do that, then you basically have this component right here, multiply with P to obtain Px, right? So you can do the same thing if you want to obtain Py. So Px would vary depending on the nx component of this unit normal vector, okay? And Py also vary depending on ny component of this unit normal vector. So once you obtain this Px and Py, you can use the previous procedure in which you have traction load acting in only one direction, okay, to compute the work equivalent traction. Okay. So in this case, you can compute this traction Tx and Ty based on this, and then just follow pretty much the same procedure to compute work equivalent traction. Okay. Now I think that is pretty much it for our two-dimensional problems. Now you can also extrapolate the same concept to three-dimensional analysis. Okay. Now for three-dimensional analysis, the difference between three-dimensional analysis and two-dimensional analysis is you would have an extra displacement in z direction in addition to x and y direction. Okay. So now in addition to only u and v function, you would also have a w function to represent your displacement in z direction. Now, along with an additional displacement field, okay, you will see that the strain components would also increase, right? So instead of having only epsilon x, epsilon y, and gamma xy, you would now have three additional strain components to deal with. But these additional strain components, if you think about them, you will see that they essentially almost they are very similar to what we have in plane problems. But now instead of looking only in x and y plane, okay, if you look in xy plane, then you see these three strain components, right? But for the other strain components, what you need to do is you need only to look on a different plane. Okay? For example, if you look on an xz plane, okay? Now on xz plane, what you would see is you would see epsilon x, okay? So you would see this component, and you would see epsilon z, okay? And you would also see gamma xz. So if you only extract these three strain components onto x and z plane, you would see that everything would be pretty much the same as in xy plane. Okay? So you can do similar computation in xz plane as you did in xy plane. Okay? But now the strain components would be different. would be called differently. From X and Y, now you would have X and Z. The same thing for Y and Z. So instead of looking at things on XY plane, you would now look at things on YZ plane. But all the computations will remain pretty much the same as in XY plane. So everything that we have seen in XY plane can be thought of as occurring in XZ plane and YZ plane as well. Okay. So you would now have 3 different set of planes to look at all these different things going on in 3 dimensions. Okay. So all the relationship that you have seen in XY plane can be used in XZ plane and YZ plane as well. But if you write everything together, okay, you would have 6 independent strain components, okay, and 6 independent stress components for 3-dimensional analysis. So you can write them together as one big equation as well. And for the elements, still based on the finite element approximation scheme, you still need to approximate your displacement field based on your nodal displacement values. Okay. So you're gonna use the interpolation function to do so, and the same information function that you use to approximate the displacement in X direction will be used to approximate the displacement in Y direction and in Z direction as well. So you're going to have the same set of interpolation functions or shape functions to approximate your displacement field in each direction X, Y, and Z. So now you're going to be dealing with a bigger element stiffness matrix. Okay. So it means bigger element stiffness matrix, more computations involved, okay, but still the same basic concept would apply. Okay. All right. So again, for parametric coordinates, okay, in addition to C and eta, so you have C and eta, now you would have another parametric coordinates, okay, which is called zeta. So you would have a z, eta, and zeta for your parametric coordinates of a 3D coordinates. So you can write your shape function based on this parametric coordinates as well. Okay. And you are going to have the Jacobian matrix that has dimensions of 3 by 3. So you can see that the computations are based on the same concept, but now because you have an additional dimension, so you need to deal with a lot more computations, and the numerical integration can still be applied. Okay. All right. So I think that's pretty much it for my part. Now I would like to talk about our last assignment. But before I do so, are there any questions regarding what we have discussed so far? Okay, if not, then let me talk about the final assignment then. In this assignment, we have a tunnel problem like this. Okay, so these are twin tunnels. So by twin, I mean everything looks exactly the same for each of these tunnels. Okay, so instead of analyzing the full problem, you can also make use of symmetry. Okay, but when you use the concept of symmetry to analyze this problem, you need to apply proper boundary conditions onto the symmetry plane. Okay. So for this particular problem, you need to include only the self weight. Okay. So you need to include only the self weight of this is rock. Okay, so you need to only include the self weight of the rock in your analysis. So no overburden pressure in this case. No overburden loading on the top of the surface. Okay, so just analyze this problem by including the self weight of rock. Now all the mechanical properties are provided. Okay, so you have this Young modulus and the Poisson's ratio of the rock here, and the geometry of the tunnel are given here. Okay. All right, and all units are shown in meters. Okay, so I asked you to use a plane strain model for this problem because we are talking about tunnels, right? So it's better to use plane strain than using plane stress to model tunnels. And I ask for this key results here. So these are the key results that you must provide from your analysis. Now, there are certain analysis checks that I recommend here. Okay, by analysis checks, it means that because you are performing a finite element analysis, so the solution that you obtain should be an approximated one, right? So how do you ensure that the obtained solution would converge to the true or the exact solution? We talk about the issue of convergence of solution, right? So how can you make sure that your solution or the obtained solution converge to exact solution? So these are some of the things that you can do to check your analysis results. But obviously, along the way, you should probably use different mesh, right? And check what's going on by using different element size in your mesh, okay? To see if you are converging to something. Okay? So performing this check means you would probably need more than one mesh, right? To see what's going on. Okay. So you should think about that, how you check this analysis results, how you could use different element size in your mesh to check what's going on. Okay. For example, first one here, okay, at section A, so it would be this section right here. So in this problem, if you want to check, for example, you cut through this structure and this plane right here. If you want to check if your analysis results are correct or not, then what you can do for one thing is you can take a look at, for example, shear, right? Then what should happen along this plane, the resulting shear force along these two planes should be 0, right? So you should see that along these two planes, the resultant shear force should somehow cancel each other. So there should be no total shear stress, right? Otherwise, if you have a total shear stress, but you have no horizontal external force, then it would mean that your structure is not in equilibrium. Okay. So if you take a look at this free body diagram that results from cutting this your structure, this plane, then you should draw certain conclusions based on this. Okay. What about sigma y? Okay, along this plane, Now you use the compute the resultant force based on this sigma y along this plane. You should see that this force should balance with the self weight of this portion, right? Something like that. Okay. And along this plane, along these two planes, would you see sigma x? No, right? Because this plane is parallel to x direction, so there would be no sigma x occurring along this plane. Okay. All right. So you should check this kind of thing to verify your answer. Okay. And there are also certain points that I asked you to look at, right? For example, this at the corners of the tunnel floor, it should be this corner and this corner right here. Okay. And for this point concerns the cutoff. The cutoff means the distance in which you choose to include in your model. Okay, so you can cut off right here at this particular distance d. Okay, also in this direction right here, you can. Okay, this is d1. You can also choose another cutoff location here. Now, what would happen if you use different cutoff, or if you use different values of d1 and d2? Would it affect the results of your analysis? So you can try to think of what you can do to make certain conclusions about this cutoff. Okay. So these are the analysis checks that I asked you to do, and the result plots that you should include in your assignment would be the stress plots. Okay. For the stress plots, there are a number of them that I asked. One is the tangential stress along the roof line. Okay, so you have to think about how you can plot this tangential stress along this roof. Okay, so along the roof line, which is right here. Okay. So in global coordinates, you would probably obtain sigma x and sigma y and tau xy, right? So these are in global coordinates. But now, if you want to plot the tangential stress along this roof, then it means that somehow you have to convert from this stress values to the tangent direction. Okay, so you have to think about that. Also, the distribution of the vertical stress and shear stress along this plane AA and A prime A prime, okay, and also the contour plots over the model for this stress complex. And I also asked you to plot the deflected shape for your model. So you also need to think about how you can plot this deflected shape to illustrate what's going on for your tunnels. Okay. All right. So the finite elements model can be done by using this commercial software. Okay. So you can either use SAP 2000 or ANSYS, which we have a license at the Faculty of Engineering. So you can select one of these two programs to perform your finite element analysis. Okay. And this is an example of the mesh that you can create. Okay. Okay. So well, this is just an example, but it may not be correct. Okay, so you have to think about how you could provide boundary conditions properly for your model. All right. So I have already uploaded this assignment on course view, so you can download it and take a look. And this is going to be our last assignment in my part. So we should probably talk about the deadline for this assignment. So our last assignment is due next week on the 11th of April. So we can probably have this assignment due one, two, three, four, five. How about, I don't know. Okay. So when you think you can submit this assignment, you can propose a date. So no one would like to propose a date for this alignment vision. So what about May 16th then? So it will be 5 weeks, right? 1, 2, 3, 4, 5. 5 weeks uh, after next week. Is that okay?
ได้ครับอาจารย์
ได้นะครับ มีใครขัดข้องไหม ก็จะเป็นวันที่ 16 พฤษภาคมเอาไว้นะครับก็ถ้าไม่มีใครขัดข้องผมขออนุญาตกำหนดเป็นวันที่ 16 นะ 16 พฤษภานะครับ เหมือนเดิมนะ 16 พฤษภาก่อนเที่ยงนะครับ ก็ขอให้ส่ง assignment ทางอีเมลเดิมที่เราใช้ส่งงานกันนะครับเดี๋ยวยังไงผมจะเขียนแจ้งเตือนกำหนดส่งไว้ในคอร์สวิวครั้งหนึ่งนะครับ so I'll put a reminder on the assignment deadline on course view so it would be on May 16th Okay, so are there any questions on the assignment? Right, not yes.
Excuse me, Ajahn.
Yes.
I have a question about assessment too.
By assignment 2. Okay.
Yeah.
So we can discuss about that later on after I dismiss other students from class.
Okay.
นะครับโปรแกรมนี่โหลดของไลเซนจุฬาได้เลยใช่ไหมครับ
ได้ครับแต่ว่าอันนี้แล้วแต่สะดวกเนาะแล้วแต่สะดวกก็ไม่ได้บังคับว่าจะต้องมาใช้ไลเซนส์ของจุฬา
อ๋อครับ
บางคนอาจจะสะดวกอย่างอื่นก็ไม่เป็นไรนะครับ
ครับผม
โอเคนะครับก็ถ้าไม่มีคำถามอะไรเพิ่มเติมก็วันที่เราจะมาเจออาจารย์เสวกชัยอีกครั้งหนึ่งก็คือเป็นหลังสงกรานต์เลยนะครับก็นัดเป็นวันที่18นะฮะเดี๋ยวผมจะแจ้งให้อาจารย์ท่านเข้ามาหลังสงกรานต์นะครับส่วนอาทิตย์หน้าก็ถือว่าเป็นวันหยุดไปนะฮะช่วงสงกรานต์นะโอเคครับถ้าไม่มีอะไรก็เชิญได้เลยครับเดี๋ยวผมจะสำหรับใครที่มีคำถามก็อยู่ต่อได้นะครับอยู่ต่อได้สำหรับคนอื่นที่ไม่มีคำถามก็เชิญออกได้เลย